Hi everyone, thank you so much for joining us for UEFI support for the Software Bill of Materials SBOM webinar as sponsored as part of the UEFI 2022 Virtual Summit. We'll get started here in just a moment. Thank you. Hi everyone, thanks again for joining us for the UEFI support for Software Bill of Materials SBOM webinar. Take a moment here to introduce everybody to our presenters. So we have Felix Polidov, who is Director of Firmware Core Architecture at AMI, and Brian Mullen, who is a Senior Manager of Software Security at AMI. And with that, I'll pass it over to the presenters for the presentation. And go ahead and unmute if you're trying to speak. Brian, I just went ahead and unmuted you, so go ahead and start presenting.
Thank you, Megan. Can everybody hear me?
Yep, we can hear you.
Great. Hello, I'm Brian Mullen. I lead Products SSDLC and PCERT at AMI. As a PCERT lead, I can confidently say vulnerability management, which is a software security function enhanced by SBOM, is something we're passionate about at AMI. I see SBOM as a vital tool in any system where assessing risk associated with software is of value. I'm working with all product lines at AMI for the purpose of creating SBOM solutions for each. Today, this presentation is going to focus on an SBOM framework developed for our UEFI product, Apptio 5. But it will be presented as an integration into EDK2 to avoid any esoteric Apptio terminology. So why are we here talking about SBOM today? The catalyst for SBOM and firmware at AMI and many supply chain partners was the Cybersecurity Executive Order of 2021. Even though the first phase of the executive order does not apply to boot level firmware such as UEFI products, this didn't deter the industry from demanding SBOM to avoid being caught off guard by a possible phase 2 of the executive order that does require boot level firmware to support SBOM. Non-compliance with the EO could result in CSPs not being able to host US federal government public data, which could result in losing out on lucrative revenue streams. When AMI started out designing SBOM, we wanted something that could be leveraged in current build system, could be leveraged by downstream partners to build their SBOM, would include support for the 7 minimum SBOM elements created by NTIA with regards to the EO, and would be extensible so that an unlimited amount of SBOM use cases can be supported in the future. The SBOM framework presented today exhibits all of these attributes. A final note before Felix and I jump into the slides, Alan Friedman, who leads CIS's SBOM efforts, continually likens the incremental process of maturing an SBOM implementation in industries to the developmental process of a child where one first learns to crawl, then walk, then run, we expect UEFI SBOM implementation development to be no different. The goal of this presentation is to detail one of many of the developmental stages of SBOM for UEFI. And this brings us to our agenda. So first, we're going to do a quick review of SBOM use cases. I'm assuming by this time, most people are pretty well versed in the power of SBOM. We're going to look at SBOM implementation approaches that we have evaluated. We're going to look at our SBOM implementation in detail, and we're going to explore ecosystem where our SBOM implementation could be leveraged. Okay, so we're going to scope this SBOM implementation to these first 4 SBOM use cases, which I think are most crucial. That's inventory tracking, software dependencies, provenance, and pedigree. So as everyone probably knows, inventory tracking is basically implements the transparency use case. It's the ability to see all the ingredients in your product. So that's covered by component name, vendor name, version, and unique identifier. And these are 4 of the 7 minimal elements, as mentioned previously. The software implementation provides support for detailing software dependencies. So software dependencies are of value as you can create unidirectional acyclical graphs. These are of values you can see if you have a vulnerability in a component. You can see how many other dependent components are affected. You can assess risk associated with maybe removing that component altogether, things of that nature. Provenance, of course, is just knowing if you have, say, for instance, an open source component, what is that open source component based on? Where did it come from? What was its version? And this is especially relevant if you make changes on top of that. That brings us to pedigree, and this is the practice of tracking any changes that you make to components. Oops, Megan, I lost, there we go. Okay, so let's take a look at firmware approaches to SBOM. This table represents different approaches in implementing SBOM. So I'll go through these, give a summary. First, you can have an SBOM in the binary. This is great because the BOM is intrinsically bonded with the binary. It's bad because it could require too much size in the firmware binary because you're adding all of that information. You'll also need some kind of tooling usually to extract the BOM. A second method is storing a reference to the SBOM in a binary. This is great because references are small. It's bad because references need to be dereferenced. So you may need one or more to develop one or more systems to actually getting the actual SBOM for that binary based on the references. And then a third approach, which I first heard about on UEFI forum, was a measured reference approach. And this is great because nothing needs to be added to the binary. You can hash the binary to arrive at a unique identifier for an SBOM. What was explored in the previous UEFI presentation is they actually leveraged TPM measurements to identify BOM components. And the drawback here is that you kind of need, again, you need one or more systems to dereference those references to arrive back at an SBOM. OCP will be digging into this method a little bit deeper, so this could gain traction in the future, but we'll be monitoring that. There's a related column here. I added some links to relevant links for each method. I included a link to the UEFI presentation. I linked to LVF, some tools LVFS created. I don't know if anybody's seen Richard Hughes's LVFS presentations, but they're really great. They're creating a lot of solutions to help secure the supply chain. A lot of these aim to use SBOMs and binary tags to empower their solutions. I definitely recommend checking out one of their latest presentations. Okay, so let's focus in on the tagging of the binaries. This bullet point, the first bullet point, it's firmware structure dependent, right? It's like, where do you put the tags? It's dependent on the structure of the firmware. UEFI has a structure. Other firmwares have their own structure. So, as mentioned, I'm looking at SBOMs across all of the product lines. They don't all, they have different firmware structures. So I have an eye for kind of looking for a common SBOM solution for all of these. If transparency is a goal with SBOM, we kind of want to come up with a solution that could be portable across different firmware image formats. So that's something we are thinking about. That's in the background. For UEFI, granularity with regards to the firmware structure needs to be considered. So if we want to use tags, how many do we want to use? Where do we want to put them? So based on the UEFI file system, we could do one per image, one per FE, per FFS, per section, etc. So these considerations need to be made. What do the tags contain? So they could contain references, as discussed earlier, or they could contain SBOM information itself. So such as binary identities, like names, version, hashes of the binary components. Okay, so digging in deeper, let's take a look at the trade-offs between each one of these approaches. And this is kind of building up to where we decided to go. So embedded identifier is basically you're basically embedding the SBOM information in the binary, and then granularity is the column. So say you do one identifier per image. I think there's limited value there. So you're looking at, maybe identifying the vendor and the version of the ROM image. Most of that information is already publicly available, so I see limited value in doing that. Let's say we embed SBOM information per FFS. That's a little bit better. It allows for inventory enablement. So we can see if you have a UEFI ROM image and you have various binaries embedded within that make up that image, you can kind of see which vendor in the supply chain modified each binary last, and you could do some analysis based on that. So there's some value there. Some challenges with that scheme, of course, is providing a chronological versioning scheme. So over time, if you had multiple tags on a binary, you could see that one binary was different than another, but you couldn't really tell which one came before the other. There's no like chronological versioning that we could see that we could make. So that was a challenge. What value there is if you know that one of the binaries contained a vulnerability, and say the hash, which we were thinking of using as a version, was different, then you could make the assumption that, or if it was the same, you could make an assumption that that other version also contained that vulnerability. So let's look at the embedded reference cases. So if you do an embedded reference per image, and foreshadowing here, this is what we went with. It provides a way to obtain an SBOM generated for the complete binary. And this works for us. Our build environment is going to build the whole binary. So during build time, we can create that SBOM, and then we'll embed the reference back to that SBOM in the ROM image. Of course, challenges here. We'll get into this a little bit more later. You need an SBOM ecosystem to be able to take that reference and identify the SBOM that it correlates to. Let's look at the per FFS references. So you have this edge case with UEFI where I guess UEFI supports the ability to upgrade individual binaries within the ROM image without upgrading the whole ROM image. I don't know if anybody's doing this, but if you are, then this is maybe something you want to go with, because you could just update that one PE file maybe, and just also update the SBOM reference that goes along with it. Of course, challenges there. You got a higher level implementation effort, again, with the ecosystem, capable of supporting per binary SBOMs. And again, with all of these with references, this is another thing we'll cover a little bit later, is that there's no guarantee. If you use a reference, you got to be careful how you use the reference, because if you don't do it right, there's no guarantee that that reference is going to be available in the future. So you want to kind of make your system to manage the references robust. For instance, if you reference a vendor and that vendor is no longer around in the future, you can't get that SBOM anymore. This is something we'll explore a little bit later. And without further ado, we'll dig into the details of our implementation, and I'd like to present Felix. Felix, take it away.
Yeah, thank you, Brian. So now that we've seen kind of a high-level overview of the use cases and different approaches towards SBOM support, let's go a level deeper and explore how SBOM generations for the UEFI firmware might work. So there are a number of challenges that has to be addressed or dealt with designing an SBOM implementation. First challenge is, I would say, there is a pretty high level of expectations. People are, at least we are seeing a lot of excitement about SBOM, and people are coming up with, more and more scenarios or problems that they want to resolve or to address using SBOM, which is great, of course. But then, essentially, it means that there is a high number of different use cases, which translates to a large number of design requirements. So the first challenge we have to deal with, it's difficult to move from design to implementation. Essentially, it's very easy to be stuck at the design phase, to keep improving, to keep trying to address more and more requirements. And then maybe the related challenge that it's very easy to overcomplicate, to come up with something, very complex. Another challenge is a complicated ecosystem we're dealing with. So the modern firmware goes through many different steps. There are many different actors involved. So I tried to come up with some sample graph of how, different firmware components, where they can originate from and how they can transition. We're dealing with typically with several open source projects. Then there is a silicon vendor that provides like a reference code for the platform silicon. That there are independent hardware vendors that may be providing some option ROMs, and of course there is a BIOS vendor who typically like integrates all those pieces together, but then also has, they typically have their own IP code as well. Then there are OEMs, then maybe some independent firmware vendors, and so on. So so as you can see, the graph is quite complicated, and I can't even guarantee that there are no cycles. Like, in fact, there are cycles in my diagram, and this is not just random set of arrows. We've seen all kinds of complicated interactions in that environment. So what makes it even more complicated that a lot of content exchange on this diagram happens in the source form, which means that changes or patches are possible at each level, in this diagram. So, for example, in industrial manufacturing, essentially, typically when you assemble a larger like device or equipment, you take your parts and you kind of combine them together. So if you have bill of materials for the individual parts, you can just essentially combine them, and here is your bill of material for your final product. So it doesn't work like this in case of firmware. Like, for example, you may have gotten your SBOM for an open source component that you're using, and it was accurate when party A received it, but when it goes to party B, it may no longer be accurate because party A may have modified something or made some changes. So what we're having here, on one hand, there is a lot of requirements. Then the ecosystem itself is complicated. Yet the design cannot be too complicated because it will not survive in such a complicated ecosystem, because there will be, as you can see, essentially each party has to contribute in order to come up with the final SBOM. And if essential instructions what each party needs to be, if we provide like a big manual how to construct a bomb, it's not going to work. It will be a lot of errors, and the information will be inaccurate. So that's another challenge, how to ensure the final data is accurate, because no matter how sophisticated the format or the infrastructure, this rule junk in, junk out, it still remains. If your input data is inaccurate, then no matter how great your tools, the output data will also be junk. So given all those complexities and all the requirements, we are focusing on a practical implementation, like what we can realistically do today and how to make as Brian mentioned earlier, like a gradual progress, step by step, just coming up with some initial SBOM implementation and then keep improving it in the future. So what we are proposing, there should be single responsible party that generates SBOM. So we are proposing to put this responsibility on entity that constructs final ROM image. Essentially, that's a leaf node and that dependency graph I showed on the previous slide. But certainly, they are not doing this responsible party is not doing it in isolation. So they will probably be using some tooling and infrastructure that comes from implementation providers, like for example, such as IPv or from the like open source community. And then the upstream partners obviously must provide SBOM for their related components. But as I mentioned, the downstream party may make modifications to the upstream components. So it's important to support some kind of a mechanism to describe patches on top of the upstream components. Obviously, there will be changes in the future to support like additional use cases. So the framework has to be flexible enough to be extended in the future, or maybe to make some adjustments. And then in order to minimize the effort and to reduce amount of errors, the SBOM implementation has to use the data that are already available as a part of the source tree, as well as some data that are specially provided for the purpose of SBOM construction. So the why do we need to provide the data, specifically for the purpose of SBOM constructions? There are two main reasons. Like some data just may be simply missing in the source tree, and then also some data might be inaccurate. For example, some like in EDK2 there are versions in every INF files, but they are not necessarily like maintained and updated. So sometimes it's necessary to override the data that is available in the source tree. So this is in brief, this picture illustrates how we are proposing to construct the SBOM for the UEFI firmware. Before we jump into the details, there are maybe two questions that we need to clarify. So SBOM provides some information about composition of the firmware, but in what terms? It could be composition in terms of the binaries and in terms of the source code. I mean, Brian already briefly mentioned it in the previous slides. So the framework we are proposing can potentially support both, but at least right now, given where we are, we propose to go with this source code. Essentially, what it means that SBOM will describe firmware components, the logical structure of the source tree, essentially, rather than like a structure of the final ROM image. And there are several reasons we have chosen this approach. So, of course, source code is a source code. So that's a starting point. That's what we use to eventually construct the binary. And in the modern firmware, the mapping of source to binary is quite complex, especially, as you know, the EDK2 is very flexible, and a lot of this flexibility comes from libraries. So most of the platform customizations are performed via libraries. And for example, the OEM may create a single library instance, but then it may end up in 55 different binaries if this is some, heavily used library. Which means what? First, it means that if SBOM is constructed for binaries, then all those 55 binaries have to have the same piece of information. It's a high level of redundancy. Then also it's a high level of complexity. The tool that constructs your SBOM has to be complicated. then if it's complicated, it means errors are likely, but then some kind of audit or review is also more complicated, because it's not always easy to say to correlate particular source files with the binaries. In case of source tree, the ownership and maybe IP isolation is more apparent. Typically, each party creates its own package, for example, and all the source code is contained over there. So that's why we think it's more practical to describe firmware composition at the source tree level. And then the second question is the level of granularity. Like how deep do we want to go? To what extent, like, do we want to describe, for example, each buildable unit or each maybe package? What is the right level of granularity? So there is no generic answer. It depends on the usage scenarios. It depends on how the source code tree is constructed. So we believe our framework is flexible. We can support different scenarios. We'll see some examples later on. So probably the optimal level is if the code developed together, there are some interdependencies, and if code has the same owner, then probably it can be treated as a single component as far as for the purpose of SBOM creation. So if you see, I'm using term components here on the diagram. So component essentially is the smallest unit described in SBOM. Now, as I said, the framework is pretty flexible. It supports heterogeneous components, so you don't have to stay at the same level. Like, for example, if your code base uses EDK2 as an external component that you just import and use as is, maybe the entire EDK2 code base can be treated as a single entity, and no need to go deeper than that. But as I said, depending on your requirements, there may be different options. At the same time, for example, if you received an option ROM, like a single driver from a third party, that can be your another component. So again, your components can have different level of granularity. So on this diagram, for the purpose of simplicity, I assume that package, EDK2 package, is essentially your component. As I mentioned, to make these things simpler, we are combining data that comes from that is already a native part of your source tree with the information created specifically for the purpose of SBOM construction. So each package is described by the DEC file, and we can leverage this DEC file during SBOM constructions. And then as far as SBOM data, we are using YAML file to provide additional information. And then there is a SBOM builder essential. That's a tool. So tool parses the source tree, collects all the extracts the data from the source tree, parses all the YAML files, then it receives some command line input. Then it generates two pieces. The main two outputs of the tool are the SBOM itself and the SBOM reference data structure. The SBOM that executive order mentioned, it doesn't prescribe a particular format for the SBOM data, but it mentions 3 formats and recommends kind of sticking with the standard format. So the good news is those all the 3 formats listed in the executive order are functional equivalent, and it's relatively easy, if necessary, to do automated conversion from one format to another. So we have chosen cycled DX, but it's not, it's easy to switch to other recommended formats if necessary. So just before going to the next slide, and then the SBOM reference data structure. This is essentially a piece of information that uniquely identifies SBOM, and it goes into the ROM image. As Brian also mentioned, it's an implementation choice whether to include SBOM directly into the ROM image or the reference data structure. Again, and at this point, we believe the reference data structure is a more practical approach. The 2 main issues with SBOM in the ROM image, number 1 is the ROM size. No matter how large those SPI chips become, size is always a concern. And the second issue, there are certain business sensitivities, like some companies don't want to broadcast information about which vendors they work with. So those maybe will get resolved in the future, but today we have to be kind of sensitive to these concerns. So let's see the essentially the executive order itself just says that everybody should have SBOM, and then there is a clarification from Department of Commerce that defines minimum elements of an SBOM. So let's see where the information for those minimum elements, how this information can be collected. So the supplier, essentially, that's an entity that owns the firmware. So we think the best option is to keep it, to pass it as a command line parameter for the SBOM builder, because it's important to get this right. So putting it in any file, there is always a big danger that people will forget to customize it. The component name and version, it can come from the YAML file, or it can be extracted from the source tree. Like, for example, in EDK2, if your granularity is package based, there is a package name and package version. If your granularity, if you would like to go deeper, and if your granularity is like INF based, you can use base name and version string. And then again, for example, in EDK2, the versions are not actively maintained, and there is a good reason essentially not to maintain them, because EDK2 is continuous development, so it's simply impractical to keep changing the version whenever a particular piece of code is touched. But then for some other packages, especially if you're getting like releases from one of your vendors, and maybe those versions are maintained there, then you can reliably use version from the DEC file, for example. But otherwise, if you cannot rely on the version, then you can directly define the version in the SBOM file. And also commit ID is another way to define version. So those different options works for different usage scenarios. For example, as I said, like for an open source projects, which is very vivid and fluid, something like commit ID may be the best options. And then for the some production based products, like for example, up to a product, we know it's important to always be able to reproduce the ROM image. That's why each component has a specific version. So it can be defined in the YAML file, or like in our case, we do have some that information in the other parts of the source tree. The unique ID for the component, again, the EDK2 already has those GUIs that's already defined. The dependency relationship. It can be described in the YAML file and using the contains tag. So we decided not to use the word dependency because it's kind of already heavily used in the UEFI ecosystem. There are those dependencies in the PI specification. There are, like, for example, library constructor dependencies. So we thought it will be less confusing to use a different word. Also, by our interpretation, dependencies contents of in context of firmware is essentially information about firmware composition. Like, for example, like a crypto package is using OpenSSL library, so that's a dependency. So but at the same time, looking at the source tree, crypto package contains SSL library. The format also supports providing additional information like such as component license, list of patches applied to the upstream components, and then also subset of the upstream component used by the firmware. The last one is important if we are talking about, enumerating our source tree. Like, for example, the OpenSSL, at least we have to keep explaining to customers that, okay, this vulnerability that you've read about doesn't apply to us because we are not using this particular portion of the library that is vulnerable. So this could be automated by providing, by expressing information about subset of the third-party component used. And then YAML is like pretty flexible, so we hope it will be easy to extend it in the future if necessary. So this is just a few examples. Just want to say that yeah, you can have different levels of granularity. Like, you can treat, for example, EDK as your one component, and also typically in every code base there are like native components, which means components developed by the owner of the code base, and then imported components. So usually for the imported component you have to provide a little more information, but for the native component your YAML file can be as short as this, like one liner is in the right corner. Like, you just need to specify essentially the name of your component, and then the rest can be extracted by the tool from the code base. Yeah, and then the result is, as I mentioned, in the standard like CycloneDX format. So I think we're running short of time. So this is just an example of a reference structure. Essentially, the purpose of a reference data structure, it should provide sufficient information so that you know whom to contact, and then once you pass this information to the owner of the firmware, to they can uniquely identify your project, the version of the project, and provide you SBOM. And then this information is also sufficient to go back and identify source tree that was used to construct the firmware. So potentially it's even possible to generate SBOM data like after the fact, maybe even with a different granularity. If certain, if your customers have a different requirements, they want a more detailed information or less details, potentially it can even be done like after the fact. And then the SBOM reference, it can be embedded, into the firmware using the FFS structures. but the data structure also has like a signature and the size, so it's potentially possible to just write a tool that scans the ROM image, just looking for a signature. And yes, with that, I'm passing back to Brian.
All right, thank you, Felix. Okay, so now we have an SBOM. What do we do with it? Or we have a binary at least. How do we get that SBOM? So SBOM framing document by NTIA mentioned advertisement and discovery. And this is the process of once you have your binary and you have your reference, how do you go about, finding where to go to get the SBOM? If we're relying on references, whatever solution you go with, you should think about it standing the test of time. So you want to avoid that reference being able to become stale or obsolete during, organizational vacillations, mergers, companies going out of business, etc. So you want to avoid, say, linking to a vendor SBOM server in the binary, in the tag. Maybe something better is a generic reference to a vendor with a generic service that maps vendors to SBOM servers. So like a system in between the actual vendor and the binary. Best, and this is probably where this is going to go, is like an open centralized SBOM repo. So I'm thinking of like, NVD for CVEs. If the federal government is going to regulate this and they're going to ensure conformance, then you're probably going to have to submit that SBOM to somewhere to get that to ensure you're compliant. So maybe something hosted by the federal government or a partner of them. Okay, so let's explore an example SBOM ecosystem using the solution that Felix detailed. So let's take a look at this diagram, and it goes from left to right. And it starts out with the platform vendor creating, basically building the ROM image. So you can see from the source code repo, you get source code, which generates a firmware image through your build process. Also in the source code repo, co-located with the source, is the SBOM YAML. And that goes through your SBOM builder, which Felix previously covered. That generates your SBOMs. Okay, so what does the platform vendor do with that? Let's say that there is an intermediate service that does the mapping of vendors to the SBOM server. So the vendor would do like a one-time registration of their SBOM server address. So you kind of got like a vendor ID to SBOM server mapping that this service could fulfill. Okay, so once you have that, you have your SBOM and your firmware images. They're released into the public domain. What if someone in the public domain wants access to the SBOM? They extract the tag. So we would provide a SBOM tag extractor. You could probably also scrape the tag out of the binary if you know how it's structured, but maybe the tag extractor does some authentication and integrity checks. So what does that tag look like once you extract it? It's going to have your vendor name, it's going to have your SBOM GUID, and it's going to have a firmware version. So I have vendor name here. I'm not sure if this is the best approach. Maybe a vendor ID may be better. And the reason for that is we already have standardized vendor ID lists out there. I think UEFI even maintains one of these lists. This SBOM service locator could leverage one of those lists. It maps the supplier identifier to SBOM server address. In this case, I just used vendor.com/SBOM. So this individual in the public domain that wants to get the SBOM, they can construct the SBOM locator, which is, you can use the GUID with the firmware version plus the server address. And you can, in this case, the SBOMs are hosted at the platform vendor. So you would take that back to the platform vendor. I foresee, these SBOMs not being public. So you probably have to do some authentication with that platform vendor to get access to the SBOM. So AMI, for instance, may, similarly to how we do our advisories, just give access to certain supply chain partners. Okay, so once you're authenticated and you get your SBOM, then you can do whatever you want with that. You can implement all of your SBOM use cases as covered previously in the presentation. So that's wrapping it up. Next steps, of course, are SBOM integration. We need to work out use cases to enable downstream partners to use and distribute the SBOMs. We need to work with upstream partners to obtain their SBOMs. And we need to expand the offering of the SBOM based on supply chain feedback. Now that kind of leads us into call of action. How do we get this feedback? I'd really like to see a working group set up for the industry so we could collaborate. Maybe this is in the form of a UEFI working group, like the security sub-team. So something we should consider. If you're interested in demos or product updates, please reach out to AMI. Upcoming, we're going to be doing some more SBOM demos at the OCP Global Summit in October. And we are looking to have this production ready for Apptio 5 by Q1 of 2023. Some resources, and that takes us into the questions. Thank you. Megan, back to you.
Great, thank you, Brian. Okay, so the first question that we have here today is, how's the SBOM data in the YALM files maintained? Does AMI plan to use an automated process to update the SBOM data, or will this be more of a manual process?
Felix, would you like to take that one?
Yes, I can take it. So it's definitely going to be automated. It's just not 100% of the information can be obtained automatically. So there will be a few pieces of information that are manual, but we're definitely looking into automating it. That's the best way to avoid errors.
Next question, how do corporate entities, nation states, or consumers verify the claimed SBOM?
Yeah, so some of these security features we haven't worked out completely yet, but as I mentioned in the ecosystem, you will have to perform some kind of authentication to get access to the SBOM in the first place. So there's some level of security there.
How are SBOMs expected to be distributed?
That is a good question. So again, I point back to the ecosystem. I would expect that leaf node vendor at first to maintain the SBOMs. So each vendor that generates the binaries would maintain a repository of the SBOMs, but I do see this evolving over time to more of a centralized SBOM repository.
Next question, given a firmware image, how does an attestation app author check the sources, tool chains, and configuration that components of the firmware were built with?
That's a good question. Looking at tool chains, Felix, how would we want to handle tool chain with relation to him?
Yeah, there are two parts, I guess. We need to get information and then verify it. So to get information, like the information is in SBOM. If something is missing, we can work on on adding it. For example, like toolchain information was not explicitly presented here, but it can be definitely added. Now, the second question is, once you have the information, how do you make sure it's correct? So, I mean, as we said, we believe this is a work in progress, but as of today, our answer is the SBOM reference data structure provides enough information to uniquely identify the source tree and specific version of the source tree that was used to produce the SBOM. And then essentially this source tree can be used to produce exactly the same ROM image, and that can serve as a proof that SBOM data is correct. But of course, if you're writing a generic tool to validate SBOM, you will not have, as of today, you will not have access to all the source codes of all the pieces of firmware. But that's something we will have to work on. During these initial stages, we believe it will be like one-to-one relationship, and you can contact the vendor and then work with them to get all the information you need.
Next question, can a supply chain partner determine the vulnerability status of a UEFI product via this SBOM?
That's a good question. So this is going towards vulnerability management. I'm not now. SBOM formats provide mechanisms to insert vulnerability status in the SBOM, but I don't think this is the way to approach it. I think you can use the SBOM as a tool to get vulnerability status for an image, and you'll want to employ what's called a vulnerability exploitability exchange, a VEX, which leads into the next question. You know, who implements the VEX, who maintains the VEX? I foresee each vendor that generates the ROM image has a VEX portal, and a consumer of the SBOM can take the enumeration data, the name of the ROM image, the version, and they can use that as input to the vendor's VEX to get real-time vulnerability status.
Yeah. I also would like to add that the YAML format we propose, it supports, you can describe patches applied to the firmware. So if certain firmware is known to be susceptible to a certain type of vulnerability, by analyzing SBOM, it will be possible to say whether patch for a particular vulnerability was applied or not. And you can specify like CVE, for example, in the YAML file to describe that these particular known vulnerabilities have been addressed in this firmware.
How could licensing information be added to the SBOM?
So they can be described in the YAML file for each component, and then for the open source component, we propose to use that standard nomenclature used by the EDK tool, that standard reference to the open source license. Then for proprietary licenses, it can be, for example, just name of the company that owns that license. Then it can go all the way down to the final SBOM in the CycloneDX format.
Great. Well, with that, we're nearly at time here. So we wanted to thank you all for attending the UEFI 2022 Virtual Summit and this presentation by AMI. The presentation slides will be available on the UEFI Forum website, and a recording of the session will be available here on Bright Talks as well as YouTube. Thank you all so much for joining us today.